Hey guys, welcome to inverse functions. Let's get started. So, an inverse function is really a useful tool, and it's something that we've kind of dealt with ever since we started learning how to solve equations. An inverse function very simply undoes the original function. And so, we can kind of get a nice little diagram. And so if we have kind of this kind of function map is what we kind of call it, and we have these inputs here, and then our function f of x takes things from the input, takes an input from our domain, goes to an output from the range. The inverse function takes us back. So the inputs of the inverse function, I'll talk about the symbols there in just a second. So the inputs of the inverse function are actually from the range of the original, and it outputs something in the domain of the original. So it has this nice kind of cyclical nature, right? So what's really cool about that is kind of the inputs of one become the outputs of the other, and the outputs of one become the inputs of the other. So we have this really cool relationship. And what's really simple is, so if we think about this circle here containing everything in the domain of f. So then this right here is the domain. I'm going to cheat and say domain of f. Everything over here is in the range of f. The inverse is flipped. So the domain of the inverse is the same as the range of the original, and the range of the inverse is the domain of the original. So we get this really cool thing. So if I know what a function is, I can find its range by finding the inverse, or the domain of its inverse. So that's really cool. And this relationship is really important. It helps us a lot. And it's not that it just takes this thing and puts it to something else over here. It takes us back to the thing that originally went there. So simply put, if x goes to y, then the inverse will take y back to x. So it's not going to take x to y and then it's going to take y to z. It goes from one thing back to itself. So really cool. And if we think about what's happening here, we can actually get kind of a really cool kind of test, if you will, for an inverse. Before I get there, actually, let me just kind of really simply this is our notation for the inverse function. So notice this -1 is on that variable, and I want to even make that even clearer. Okay, so we have f to the negative first power of x. And the way we read this is simply, this is f inverse of x. And so it's really, really crucial that we recognize this is not the same as this. These two things are not the same. And why are they not the same? It comes to a simple fact that the -1 here is applying directly to the function name, whereas here the -1 exponent is applying to the output of this function. And so here, this is just going to be whatever this number is raised to the negative first power, but this is the inverse function. So really crucial that you kind of are careful with how you draw those, how you write that out. Okay. So there's kind of a little quick notation for you. Let's get back to this example. So if I start at x, I put it into f, comes out as y, I put that into the inverse, it comes back out as x. So let's write that. So we take x, put it into f, comes out as y, put it into the inverse, and it comes out as x. Does this look familiar to anyone? It does, right? That's function composition, right? Exactly. And what's really cool is we get this kind of test, if you will, for whether or not two functions are an inverse. If two functions are inverses, when we compose them together in either way, they equal x. So whether we do f of f inverse of x, that will equal x, or f inverse of f of x, that will equal x. Doesn't matter. And so what we can do is, let's say I say, here's a function f and here's a function g. Are they inverses of each other? Well, we just check. Do their compositions equal x? Let's do that. So let's let f of x equal, let's do 4x plus 9. And g of x, actually let's do 12. Let's do g of x equals 1/4 x minus 3. Okay, so I have two functions. I want to know, are these two functions inverses of each other? Is f the inverse of g and g the inverse of f? And if they are, then we get to really do some kind of fun things with them. So what's really nice and easy about this is all we have to do to verify if they're inverses is figure out what does that equal. Well, the first thing is to rewrite from composition notation into function notation. So we get f of g of x. Now order of operations says start with x. X is x, I don't know anything more, but I know what g of x is. G of x is 1/4 x minus 3. So I can get f of 1/4 x minus 3. So I just replaced g of x with what it's equal to. So because g of x is equal to this, I can just replace them one for one. Now, function notation says this is f of whatever is in here, f of blank equals 4 times blank plus 12. The blank here is now 1/4 x minus 3. So we get the expression 4 times 1/4 x minus 3 plus 12. We just want to simplify, so we multiply the 4 in, so we get 4 times 1/4 x gives me x. 4 times negative 3 gives me negative 12. And then we don't forget our plus 12 out here. Simplify one step further, and negative 12 plus 12 is 0, so we get x. They must be inverses. But we didn't check the other way, right? And we know that just because f of g of x equals x, that doesn't mean that g of f of x is going to equal x. So we have to check the other way too. So, I don't have a lot of board, so we're going to erase this. So we're going to look at g of f of x this time. So again, we start by rewriting from composition notation into that function notation. We replace our f of x with what it's equal to. And then we evaluate g when x is 4x plus 12. So we get 1/4 times 4x plus 12 minus 3. Distribute, we get x plus 3 minus 3. And plus 3 minus 3 go away, we get x. These are inverses of each other. Yes, that's awesome. So, let's talk a little more about kind of the concept of inverses. So I know how to check it to see if two functions are inverses or not. It's really easy, we just compose them together. Okay, but how do I know if a function is going to have an inverse? Like, can I just look at a function and go like, that one's got an inverse? And the answer is yes. And the answer, first of all, is every function has an inverse. The bigger question is that inverse a function? And so to answer that, we have to ask ourselves, what is a function, right? Might be something way in the back, I've got to pull it out front, right? A function is any relation such that for every input, there's one output, right? So we'd say that f is a function if every input has exactly one output. Okay? Definition of a function, day one. So, every input has exactly one output. Now, I'm going to do something here. f has an inverse function if every what? Now, f was a function if every input has exactly one output. So now, let's think about this. We're talking about the inverse, right? Remember, the inverse goes backwards. So what are the inputs of the inverse function in relation to f? Well, if you remember those two circles, right? The f had the input to the output. Well, the inverse took one of those outputs. Oh. So f has an inverse function if every output has exactly one input. That's awesome, right? That's so nice and that makes sense. Because a function is a function if it takes one thing from here to one thing here, right? Nothing here can go to two different things. Now, it was okay if two different things here went to the same thing, right? Think x squared. Negative 2 and 2 both went to 4. But for it to have an inverse function, it means that every output has to have exactly one input. So that when I look at the inverse, right? So if I think x squared, right? If I think the inverse of 4, well, that's not just 2, but it's also negative 2. That's not a function. So we have to have that also, that every output has exactly one input for something to have a function, an inverse function. And this is called, this feature, if a relationship or a function has, every output has exactly one input. So we say that if every input has one output and every output has one input, then we say that the function is 1 to 1. Okay? If these conditions are met, our function is 1 to 1. If every input has one output and every output has one input, our function is 1 to 1. And we have an inverse function. For the rest of this class, we're only going to want to deal with things that are 1 to 1, the rest of this lesson, so the entire class. For the rest of this lesson, we want to talk about functions that are 1 to 1 because they have inverse functions. And we know that functions have those kind of innate built-in kind of structures that just a general relationship wouldn't. I wouldn't want to deal with the inverse function of x squared because the inverse function of the inverse of x squared is plus or minus the square root of x. And that's not something I want to deal with. I don't want to have to deal with that plus or minus. So, how can I check this? I mean, if I know this, that's great, but how can I check it? And the easiest way to do that is by graphing. Here's just a random graph. Now, how do I know this is a function? What do I use to tell if this is a function? Right? We use that vertical line test, right? Some of you guys have heard that maybe. Right, that vertical line test simply says if I draw a vertical line anywhere along this graph, it's only going to cross the graph once. And what that does, okay, is that says at this input, if I only cross once, that means I have one output. So for every input, there's exactly one output. If I crossed twice, that would mean that for that input, I have more than one output. We're not a function. So that's the vertical line test. Now, an inverse function just flips our inputs and outputs. So instead of our line going this way, it goes this way. And this means that at this output, we have this corresponding input. So to check to see if a function is 1 to 1, we do the horizontal line test. And that's just the exact same idea as the vertical line test. If it crosses the graph twice, it's not 1 to 1. If it crosses the graph once, it is 1 to 1. It's that easy. Now we can ignore my terrible swooping drawing, right? This goes out. So that's how we can check to see if a graph of a function is 1 to 1. Okay? And if we don't have the graph, we can use our calculators or Desmos or all of these technologies to get a graph and look and see, is this going to pass the vertical and horizontal line test? All right. Now, let's find an inverse. Let's talk about how to find it. Now, there's two things I'm going to talk about. One is kind of something that you're going to see in a lot of other videos. If you look to other videos or if you look in books and things like that, you're going to see this way. I personally hate this way, and I'll mention it, but I'm not going to do it on board. And so I just want to make sure you're aware. And so when we're finding an inverse function, the first thing we do is we take our equation, set it equal to y. Okay? So let's say our function is f of x, and that equals, say, 5x minus 13. I want to find the inverse of this. I know it exists. This is a linear function, positive, right? So it's going up like this. That is definitely going to pass the horizontal line test. So to find the inverse of this, the first thing I do is I set it equal to y. And this is the same in the other process that I was talking about. Where that other process differs from mine is they say to then switch your variables. So you would then rewrite this as x equals 5y minus 13. There is no mathematical reason to do that. The only reason to do that is because basically teachers in past years have thought, not in say last year, but like past teachers, the ones who are writing the textbooks now, basically like, well, students aren't capable of solving for a different variable other than y. If there's x and y, they only solve for y. And that's ridiculous. You guys are smart, intelligent people. You can solve for whichever one you need to. So we're going to leave it like this, and we're going to solve for the input. And the reason I like to do this is it maintains that relationship of the input of our function is x. Well, when we're done solving this, the input of our inverse will be y. And it maintains that relationship of the input being the input of the function is x, and the output is y. But the input of the inverse is y, and the output is x. So it maintains that kind of cyclical relationship. So if you want to switch them, and that's something you're comfortable with, I'm not going to mark you wrong. It's going to accept either answer, but know that I'm not going to do that on my notes. So now all I have to do is solve for x. So we take our equation, set it equal to y, solve for x. That's all we're doing. That's all it is. So I'm just going to add 13 to both sides, giving me a y plus 13 equals 5x. Divide by 5. Now, this is a perfectly sufficient answer. You can also split this fraction. So if you are remembering how to add fractions, right, we had to get the common denominator, right? So if I had, like, say, 3/5 and 4/5, right, we'd add those together, we get 7/5, okay? We can split this, and what we end up with is y over 5 plus 13 over 5. Okay, and we can actually go a little bit further too if we want to with some different things. Y over 5 is really just 1/5 y plus 13/5. And so any one of these are all correct. These are all good. Okay. I wanted to show all of them to you so that way if you see them in an answer or some example online, you're like, wait, I got these, but I got this, but they got this, or some combination. You're still good. They're all equivalent answers. Okay. So our final answer to this question, right, which was find the inverse of f of x, you would say something along the lines of f inverse of y, because notice our input is y, equals y over 5 plus 13 over 5. And again, use any of these three forms you want, it's going to accept the answer, you're good. So that's how we find the inverse. It's pretty easy, okay? Now, let's do something hard. let's find the inverse of this. Now, for those of you who are going like, is this even 1-to-1? It is 1-to-1. The graph kind of does one of like these sorts of things. So it's still going to pass that horizontal line test and that vertical line test. So all we're going to do, this is going to be one of the hardest algebraic things you do this entire term. When I say algebraic, I mean like with the manipulation of variables and numbers, kind of moving them on sides of equal signs. We do this the same way. It's really simple. We set it equal to y. And now solve for x. Now, the thing you'll notice is there's two x's here. I want to think, like, let's pull ourselves out of math. And let's say you're in Salem. You've got some random person come up and says, hey, how do I get from here to Portland? You don't want to tell them, all right, so what you're going to do is you're going to drive up to Portland, and then you're there, right? Or like, all right, you're going to drive up to Keller Auditorium, and then you're going to go left and right and do this, right? You don't want to tell them how to get there by getting there. The same thing with a variable. We don't want to define x in terms of x. So when we have a problem with multiple variables that we need to solve for, like here we have two different x's, but we need to solve for that x. We have to combine it so that we have a single x term. And the way we do that is through some simple algebra steps. So let's walk through them and see what happens. The first thing we want to do is we want to get rid of this fraction. So I want to multiply both sides by 2 plus x. So when I do that here, those cancel out. Okay? I'm left with 3x minus 2. Now over here, I'm going to kind of jump a step as well. I want to distribute this because I don't want this x trapped in the parentheses. So I'm going to take y times 2 to give me 2y, and then y times x to give me plus xy. Okay? So for the purposes of this problem, y is a constant, just like 3 or 5 or 7 or anything like that. We're going to just basically ignore it as part of the x. So if I had an equation, let's kind of cover this up. If I have an equation where I've got an x on both sides, what do? Right? We need to get all of those x's onto one side, right? All of the terms with what the term we're looking for, the variable we're looking for on one side of the equal sign, and everything else to the other side. And that's what we want to do here. Okay? And at this point, I'm going to put a little star here. Instead of that, I'm just going to write it again over here. Okay? Because depending on what we do here, we're going to get two answers that look different, but they are still the same. There's no right or wrong way to do this. And so I want to kind of do both ways and kind of show you what happens. Okay? So we are solving for x. So I need to get the x's onto one side. So it doesn't really matter which way you go. So let's just move the x's to the left, non-x's to the right. So I'm going to subtract 2y from both sides. And I'm going to subtract 3x from both sides. Those cancel and those cancel. And what I'm left with on this left-hand side is xy minus 3x equals negative 2 minus 2y. And we're almost done. I've got my x's on one side, right? Normally, if we could, we'd combine them into a single term, right? But the problem is this is an xy and this is a minus 3x. These aren't like terms, so I can't combine them. But what I can do is these have a common term. They both have an x in them. I can factor that x out, okay? Kind of the reverse of what we did here. Here we had 2y plus xy came from that 2 plus x times y. So what I'm going to do is I'm going to factor out the x. And when I do that, I'm left with y minus 3. Now, I went from this equation where I had an x in the numerator and an x in the denominator, and now I have a single x term, single x value. All I need to do is get it by itself because it's multiplied by this quantity, y minus 3. So I just divide both sides by y minus 3. Giving me this lovely final answer of x equals negative 2 minus 2y, all over y minus 3. Okay? So this process here is one of the most complicated things you do. Right? If you're looking at it, you're like, man, there's so much, right? But if we just go back and step by step, it's really easy, right? We started by taking this function, setting it equal to y. Then we got rid of our fractions, and we simplified everything that we could, right? Got rid of all the parentheses and everything like that. Then we got the variable we were looking for onto one side, all the terms without that variable onto the other. And then here's the trick. We factored the variable that we wanted out. And then we just divided. It was really simple. Okay? Something that looks really crazy and really scary and complex, but it's really a simple thing. So now let's see how I can do this differently. So over here, I just moved the x's to the left because a lot of times that's where we have the variable we're working with. But I actually see over here, I have a negative 2 over here. If I can make things positive, I like to. So I'm going to add 2 to both sides. And so that moves my non-x terms onto the left, so I need to subtract xy. And so on the left-hand side, I'm left with 2y plus 2 equals 3x minus xy. So very similar to what we had over here, except the things are on the opposite sides and everything's opposite sign. And so again, I have no x's here, I have x in both of these here, but I can't combine them because they're not like terms, but I can factor that x out. So I get 2y plus 2 equals x times 3 minus y. Pretty much the same thing we got here. Again, to get x by itself, we just divide by 3 minus y. And we get our final answer, 2y plus 2, 3 minus y equals x. Do these look like they're the same thing? Because they both equal x, so they must equal each other. Do these look like the same thing? Are these equal? Looks like a terrible question mark. There we go. Well, I mean, just right off the bat, I'd have negative 2 here, positive 2 here, so we're like, no, that can't be equal, right? But notice, negative 2, positive 2. Negative 2y, positive 2y, positive y, negative 3, positive 3. So for every single term, they're all the same terms, right? We have a 2, a 2, we have a 2y, a 2y, a y, a y, a 3, a 3. All of them here are the opposite signs as they are all over here. And so these are the exact same thing. The difference is essentially if you multiply this by negative 1 over negative 1. You're just changing all the signs, but you just multiplied by 1, so you didn't change anything. The reason why this happens is very simply whether you moved your variable to the left or to the right. So if you're looking at things and you're like, man, the answer key has this answer, but I got this answer, you're not wrong, and it'll accept that, right? And definitely on a test, that will be an acceptable answer. So make sure that you guys are going through and carefully working through your work, but if there's a little difference, double check. What is that difference? Are you just totally wrong? Are your numbers different? Are your signs different? What's going on? Are some of the signs the same, some of them different? Those are problems. But if all of your terms are the same and all of your signs are opposite, you're good to go. So what this tells me is that G inverse of x equals 2y plus 2 or 3 minus y. Ooh. G inverse of y. There we have it. We have found the inverse of this crazy function. This is one of the most algebraically intense problems you do. You do not have to do both. Do not do both. This is just demonstrating for you. Do one or the other, not both. Okay. Now with this same problem, I want to do some more. So, what type of function are these? Well, we've got a linear function over a linear. That's a rational function. You guys love those, right? Right? I know you do, right? Yeah. Yeah. Rational functions. They're not bad. we know how to find domains of rational functions, right? It's everywhere where the denominator is not 0. So what's the domain of g? Well, as long as the denominator is not 0, we're good, right? And when is denominator 0? 2 plus x, so that's at -2. So it means our domain is -infinity to -2, -2 to infinity. One thing we didn't do, what's the range? I have no idea. I don't know what the range is. I mean, just looking at this, I don't know how to find the range. But you know what you can do? Is if we think back. Right? Domain, range. The range of our original function was the same as the domain of the inverse. So to find the range of this function, I just need to find the domain of this. What's the domain here? Well, the domain here is, again, everywhere where the denominator is not 0. The only time the denominator is 0 is when y is 3. So it's everything except 3. So that's the domain here. Which means that's also the range here. So that must mean then the range here that's it. There you go. You have it. That's inverse functions. Inverse functions are really important to kind of understand. There's something that's going to be really useful in this idea of kind of going from A to B, from B to A, kind of this circle, cycle. Okay, it's a really important idea and concept to understand about inverses. Okay, it's going to come up if you ever take a stats class. We're going to do inverse things in there, and you're going to have to kind of, that concept is really helpful to understand. Not finding necessarily inverses, but use that concept of an inverse. We're going to use it in this class. We're going to use it in our next sections. We're going to talk about exponentials and logarithms next week, and those are really cool because they are inverses of each other, and we can do so much fun stuff with both of those. So make sure you guys go through and understand how to find these. I can guarantee you on your final, I will ask you to find the inverse of something exactly like this. Okay? We'll give you a rational function like this, and I'll say, find the inverse, and you will need to give me this answer. And then I'll probably even say, hey, what's the range of that guy? Okay? So, make sure you guys learn how to do this, practice those ideas. A lot of the homework is really just kind of conceptually working through it, going inputs to outputs, outputs to inputs, using some graphs and some tables even. And that's really a simple idea, hopefully. I'll do one example with you real quick. Let's say here's our function f. I said, what is f inverse of 17? Well, this is the inverse, right? That means 17 is the output of our original. So we're 17 and we're asking what's the input. So that equals 1. What's f inverse of 1? That's 2. Now, what about this? What's f of 1 to the negative 1? Order of operations, right? Because we've got two parentheses, so we've got to kind of be careful, right? This negative 1 is not applying to our function name. Not like it was here. Not like it was here. So what I have to do is I first have to find what is f of 1. Well, f of 1, that means x is 1, f is 17. So this is (17) to the negative 1, because I know what this was by using the table. All over. So I can replace that. Then I just use the exponent rules. See, this is just a number with an exponent. So this is just 1 over 17. That's it. Alright, you guys. You guys have everything you need to crush this homework. I look forward to hearing from you guys. Make sure you guys get that quiz done on Sunday. Good luck.